Hello everybody! Allow me present you my contribution with name Modeling of Stator Coil-To-Ground in Induction Motor. I cooperated on this topic with Mr. Stanislav Kocman. We are from Department of General Electrical Engineering, which is part of Technical University of Ostrava in Czech Republic. Our development generally concerns induction motors with using FEM modeling. This is also the case this presented paper. If we generally focus on faults arising in the manufacture or operation of induction motors, can divide them into mechanical faults. This group includes inaccuracies, manufacturing tolerances, problem with bearings, and so on. Second group is found in power systems. There are most frequently undervoltage, overvoltage, failure in power supply, and generally we can say power quality. Third group are electrical faults. When we generalize again the description, main group are stator and rotor windings problems. For our development, we are considering squirrel cage rotor, hence the problems with the casting of aluminum into rotor bars and into short circuit rings. For stator, this is the topic of faults in stator winding and therefore in its insulation system. These problems are represented coil-to-ground faults. We have therefore demonstrating or development for this topic. As mentioned in the previous slide, we did induction motor with squirrel rotor cage. It is a standard manufactured serial motor which has high 112 nominal power output 4 kW, connection to star. Selected parameters are presented on this page. In previous development, we worked with this motor, especially we use FEM modeling with software COMSOL multiphysics for assembly basic models and tuning model for real parameters. Our investigations were further made with using previous models. Next steps were created new change models with using COMSOL multiphysics software. Regarding new models, first 2 points were based on the work already done. New procedure considered of creating faults in the winding tuned motors. The same procedure were preparation for 5 different points of fail. For better understanding, we can see idea circuit diagram on right side on slide. The individual coil-to-ground faults points were always performed for the same phase, as we can see phase A. The simulations have been carried out for the motor loaded with the nominal torque 27 Nm and with considering direct online connection. After start and before connection coil to ground, we can see that waveforms currents for steady state operation are steady and acquires the same value. This we can see in left side on slide. On the right side we can see layout of magnetic flux density and equipotential lines of magnetic vector potential. This behavior is typical for a healthy motor with steady state operations. After the disappearance initial transient effect occur the steady state. Steady state is described on previous page. Next step our modeling considered of inclusion coil-to-ground fault. They were realized in time approximately 0.53 seconds after start. Affected phase A, we can see from current waveform that the value is very high with compared to other unaffected phase. Regarding torque, we can see that in value are high oscillation and RMS value of torque is on value 10 Nm. In reality, this situation would be lead to react protect equipment in affected phase, which would to lead into phase motor operation or react protect equipment for all phases and stop of the motor. This slide presents waveform of current for a different point of fail coil to ground. It's evident from the individual waveforms for point of fail 1, 3, 5 that the value of current if affected phase increase. The increase in value is higher for each point and increases as it approaches the motor connection point to power supply. Also, the phase shift of the affected phase is not 120 degrees compared to other unaffected phases. On the left side, we can see failure ground to coil 4.1 correspond with idea diagram on page 3. In the middle is fail point 3 and on the right side is fail point 5. Concerning magnetic flux density and equipotential lines, the pictures on the slide correspond for magnetic flux density and equipotential lines with currents on previous page. A simple look can again be seen that with increasing the distribution magnetic flux density and magnetic vector potential is more unbalanced, which compared to ideal case for a healthy motor on page 4. This fact corresponds also with previous page when the current in affected phase increased with point to fail. When we compare current imbalances in depend on point of fail, we get waveform on left side. We can see that current in affected phase increasing up to 80%, 4.1, and up to approximately 120%, 4.5. The most current imbalances is 4.3. When we express stator currents, we can see that point 1 is least unfavorable and point 5 is most unfavorable. This is also applied for influence affected phase toward unaffected phases, as can be seen from the picture on the right side of the slide. Next comparison we made also for inner torque and also for speed. We can see that influence of inner torque is very small, on torque is still constant. This situation present picture on left side. Regarding to speed, we can see that point 1, 2 and 3 don't have essential influence on speed. But from point 4, the speed decrease and 4.5 is speed value approximately 1000 revolution per minute, which can be for most applications unacceptable. In conclusion, I would like to say that our investigation of motor failures coil-to-ground in relation to the point of the failure is a nice example of the use finite elements method modeling in practice, because there was no need to solve any prototypes or measurements. It was necessary to have a suitably tuned physical model to verify the modeled facts. However, in my opinion, reality would be very similar to modeling. As for the results themselves, the current in the fail phase always increased greatly, and the fail also affected the other parameters mentioned in the paper. The difference in values between the fail coil-to-ground point at the beginning and the end of the winding is also very marked. Further research will also examine in detail the effect on other phases and various combinations of fail in other phases. Thank you for your attention, and thank you for the opportunity to present my contribution on your conference.